Well, hello everyone. My name is Peter Rijt, and I'm the chairman of the Energy Club. Thank you all for tuning in today to our lunch lecture. This is already our second to last lunch lecture of this year, and of course we have many more events coming up after the holidays. All these events and even new job opportunities and internship opportunities are posted on our website, theenergyclub.nl. And with me today, I have a board member of IOLIS, is Maarten, and he is the board of the European Wind Energy Master Program. He will give a short introduction in a moment. And then we have our keynote speaker, who is René Bos from Eneco. He's a former SET student, which has a PhD in wind energy, and currently is the packet manager at Eneco. He will give you a short introduction to the future of wind energy. And then of course, we have enough time to answer all of your questions. So if you have questions during the lecture, please post them in the chat. So afterwards we can fluently go through them. And yeah, we have enough time to answer them all. So now, Marta, I want to give the stage to you. Let me see. There we go.
Thank you. Hi guys, my name is Maarten. I'm the vice president of ISA AOLIS, the study association of the European Wind Energy Master. I'll shortly share my screen. If that's working. Can you guys see my screen now? Nope. Peter, can you enable screen sharing?
Yes, you're a co-host now.
Great, thank you very much. All right, so thank you for the invite, Energy Club. I'll keep it short, as asked. So the European Wind Energy Master is a 2-year, of course, specialized wind energy master. We have students from many backgrounds from all over the world. It's a double degree program in 4 tracks, which are electrical power systems, offshore engineering, rotor design, and wind farms and atmospheric physics. And it takes place at different universities. DTU in Copenhagen, TU Delft in the Netherlands, of course, the University of Oldenburg in Germany, and NTNU in Trondheim, Norway. And it's double degree. The website and email for contacts are on the page. I think you'll get the handout of the presentation after. And then AOLIS, like I said, we're the student association for the program, and our aim is to enrich the experience of the students in the program. We do that through educational, career-oriented, and social events, among others, through lunch lectures like these, but also excursions to companies. We have the multiple day excursion. And normally, when there's no COVID, we would also have social events like drinks, a Christmas dinner. Our members, all of our students in the program are a member at the moment. 50 people from around 14 countries, and we have 100 plus alumni, that are still in contact with the association. If you have any questions about the program or about AOLIS, or if you are a representative of another association and would like to cooperate, please feel free to reach out. The email and website are on this handout as well. I think that's it. Have fun with René's lunch lecture, and thanks again for having us.
Yes, so René, I think it's up to you now to share your screen. I guess the floor is yours.
Yeah, thank you. Let me just share everything. I hope everything is now visible. So good afternoon. My name is René Bos from Eneco Offshore Wind, and I'll be telling you a more or less general story on offshore wind from our perspective. So let me just start off by telling you something about myself. So my entire academic career has been at TU Delft. I started in 2006 with the Bachelor Aerospace Engineering. Then I did the Master Sustainable Energy Technology, and I followed this up with a PhD at the Wind Energy Group. Then I joined Eneco. I was one of the guys to join after the award of the Borssele 3 and 4 permit. And since then, I've been part of the design team of Borssele 3 and 4, but also recently Hollandse Kust Noord. And I've been involved in all major offshore tenders of Eneco since then. My focus is mainly on conceptual design and tender development. So what I do is I write tender bids, I do wind farm design and optimization, I do a little bit of contracting, and I spend a good portion of my week also on innovation. Besides that, I'm also the contact person within Eneco Offshore Wind for internships and master projects. So today I'm going to talk to you about offshore wind. So this is an aerial picture of Luchterduinen. And Luchterduinen is our second offshore wind farm. It's located off the coast of Katwijk. You can actually see it from Scheveningen. This is a view from the north. And what you don't see in this picture is here you see everything above sea, but what you don't see is all the work and equipment that goes along with it. So I've shamelessly stolen a YouTube clip from the port of Rotterdam that in 1 minute gives you a bit of a taste of what the offshore wind sector looks like.
Outstanding services, excellent facilities, and the world's best infrastructure have all contributed to establishing vibrant business opportunities for the offshore wind industry here in Rotterdam. Rotterdam offers ample room for initiatives in offshore wind, as wind energy is a vital component of the energy transition. Here you will find state-of-the-art component manufacturers and production facilities, world-class contractors that can handle any job of any size, leading experts that provide excellent training and education, an innovative mindset and institutions to explore new possibilities, and service providers that create a perfect business climate. Our ever-growing network of partners helps your business thrive. We foster a spirit of cooperation, so together we propel your business ahead and into the future. Offshore wind in Rotterdam, generating shared success. Make it happen.
So what you see is that with offshore, we are used to working with big equipment, big machines. And I assume that you know how wind turbines work and how wind onshore works, but why exactly do we want to go offshore? And there are a couple of major reasons for this. First and foremost, the wind speeds are higher and more reliable. So the variations from hour to hour and from year to year are less strong than what you see on land. In addition, there's plenty of room to go big. So we have the space to build big projects and to install big machines. And we don't have the trouble of low bridges or if we need to cross a roundabout with a wind turbine blade, for example. And also that a large part of the population of the world actually lives in coastal areas. And that means that we have to transport the electricity over a much shorter distance. This of course changes if you go further offshore, but that's another topic. And there's also less competition for space. So even though there is competition for space, and I will share another slide on that later, there is far less trouble in securing an area than it is on land. So how does a offshore wind farm actually look? The last couple of projects that we did as NACO is roughly coupled into 3 blocks. So on the top left, you see the wind turbines. So wind turbines are supplied by a single manufacturer, and they design, fabricate, and install tens to hundreds of turbines. Then the yellow block is the balance of plant. So the balance of plant is actually everything that you need to support the wind turbine generators. So those are the steel foundations, the boat landings, the external platforms, the inter-array cables, up to the offshore high voltage station. So that's in the green block. In the Netherlands, the offshore high voltage station is designed and installed by TenneT, so the Dutch transmission system operator. In Belgium, for example, it's Elia, and in Denmark, it's Energinet. And in the Netherlands, it's TenneT who builds the offshore station and also the export cable to the onshore land station, and then transforms it to 380 kilovolts, so to the high voltage grid. So just a little bit about Eneco. So Eneco, together with RWE and Vattenfall, we are one of the largest energy producers in the Netherlands. So we supply gas, electricity, and heat. We supply to about 2 million Dutch households and companies. We trade around 30 terawatt hours per year. And since this year, we are owned by Mitsubishi Corporation and Chubu Electric. And prior to that, we were owned by a large number of Dutch municipalities. So we were the last electricity company to be publicly owned. Some of our famous clients also include TU Delft and the Dutch railroads. So TU Delft actually buys the electricity from the Luchterdijnen wind farm that I showed earlier. And in our portfolio, we have a lot of onshore wind, we have a lot of offshore wind, and next to that, we also have a lot of solar, mainly rooftop, a biomass plant, and a couple of conventional plants. And especially the offshore wind part is rapidly growing. So currently, we are involved in 6 offshore wind farms in the Netherlands and Belgium. Our first wind farm was Princess Amalia Wind Park. It's been operational since 2008. Next, in 2015, we constructed Eneco Luchterdijnen. And then after, it was Noorder, Borssele 3 and 4, Seamate in Belgium, and most recently Hollands Kust Noord. So if you look at the development stages of an offshore wind farm, there is usually a development process where you at first you prepare a bid. So in a lot of countries, it's actually the government that writes out an offshore wind tender, and it is up to several parties to write a bid in order to bid for a concession or a permit. That's usually what you start with. So you start with a bunch of conceptual designs. You put together your business case, and if it's a price tender, then it's up to you and your management to decide how low you can go. Then if you win the tender, then it's you go into the detailed engineering phase. So together with your contractors, your wind turbine and your balance of plant contractors, you detail out the design. You figure out how much steel you need. You figure out what the requirements are from the transmission system operator. And then you prepare up to the point where you have a design freeze and you can start ordering your major components. So that's what you call financial close. So financial close is the point where everything is there. Your entire financing structure is in place. And that's the point where you start to order your big components. And that's when you start getting the money from your lenders and when all the loans start. And then afterwards, you go into a construction period. So that starts off with manufacturing the components. So the big components can take up to months to years to fabricate. And then you start installing them offshore. And when everything is there, you do a couple of trial runs to make sure everything is okay. And if everything is all right, then as Eneco, we take over the asset and then we operate it for about 25 to 30 years, depending how new and how new the asset is and in what state the asset is after 20 years. And then we decide whether or not we extend the lifetime or if we decommission it. So an offshore wind project is, the way we see it is structured in this way. So in blue, you have the project, and in many cases, a project like Blauwind is for Borstel 3 and 4 is a special purpose vehicle. So it is a separate legal entity where we place specialists. So we outsource finance specialists, contracting specialists, legal specialists, or engineering specialists, such as myself. We have relationships with local stakeholders, government, and the transmission systems operators. So those are external parties that we get a lot of our design input from. Then we have relationships with investors, with lenders. So we get funding from investors and lenders, and in return, we give out dividend or we pay interest. Then the project sells the electricity to an electricity offtaker. So usually these are trading houses, or it's trading houses, or via a trading house, we sell it to a big company. And this is where the project gains its income. And then on the bottom, you see the major contracts and the major chunks of expenses that you have. So you have a balance of plant contractor. That is a big expensive contract. Usually the most expensive contract is the wind turbine contract. And then you also have asset management, and you pay a big chunk for operations and maintenance. So this is one of the views that you can have. Other parties like Ørsted and Vattenfall, they have different views on how to structure a project. This is usually ours. And if you see what Eneco is involved in, as Eneco, we are primarily an electricity offtaker. So our trading house, Eneco Energy Trade, buys the electricity. We are also an investor. So that means that we own part of the wind farm. We deliver all kinds of specialists to a project. And from IJmuiden, we do the asset management. And for Princess Amalia wind farm, we also do the operations and maintenance. Now, last summer, we won, together with Shell, we won the Hollandse Kust Noord wind farm. And that in many, it is a bit of a special wind farm in the sense that it is the third wind farm to go in the Netherlands at zero subsidy. But it will also be a wind farm that will be delivered in record time. So the Hollandse Kust Noord wind farm, we won that last summer, and it will already be operational in 23. So that means that in the period of a little shy of 4 years, we will have designed, procured, fabricated, and installed almost 760 megawatts of offshore wind. And next to that, there's also a big innovation package attached to this. So if you look at all the types of innovations that we will install, we will have a pilot to develop new and exciting wind farm control strategies together with TU Delft. We will install a floating solar farm within the wind farm, which makes it a true hybrid wind farm. And we will also experiment with offshore battery and hydrogen storage. And I want to dedicate actually the remainder of this talk to talk about scale. So offshore wind is a renewable energy source that is very big, large, and you can truly build it at scale. If you look at all the projects that have been installed over the last couple of years, you see that it grows exponentially. You can actually plot it on a logarithmic scale. And you see that the trend is actually you see that over the last 15 years it has been doubling steadily at a rate of every 3 years, and that is actually very quick. And that is partly due to the project size, but also partly due to the size of the machines. So here I will show you two pictures. So the left one was taken in 2015 at Luchterduinen, and the right one was taken this summer at Morselen 3 and 4. So to the left you see a V112. It is a 112 meter diameter wind turbine with a 3 megawatt rated power. And to the right, it is a V164 with a 164 meter rotor and 9.5 megawatts of power. And the vessel that you see installing it is actually the same ship. It is the Van Noord Aeolus. And just to show you how rapidly machines have grown over the last couple of years. And this is also what you can see here. Especially offshore, there is plenty of room to grow. And since Luchterduinen, you actually see the V112 was one of the first dedicated offshore machines. And over the last couple of years, you really see that offshore wind turbines have broken themselves loose from their onshore counterparts and have really started their own class with their own design requirements. And so the blades are longer, the generators are bigger, the machines are heavier. Since last year, there is the largest wind turbine in the world is now installed on the Maasvlakte in Rotterdam. So that's a 12 megawatts, 220 meter rotor, and already bigger machines have been announced. So why go bigger? So in this slide, I will try to explain to you a little bit why it pays off to go bigger. Because if you look at the expenses you make in an offshore wind farm, there is a level of fixed cost. So that is usually stuff like project management, that is the risk, that is for a large chunk, it is the cost of financing. And on top of that, you have per unit costs. So for every wind turbine and foundation you install, you have to install, for example, lights, or you have to, with every turbine you install, the risk increases, the installation cost increases, and then the balance of plant. So that means the foundation and the inter-array cables, they grow with size. So the monopiles, they become bigger as your turbine grows bigger and heavier. But if you go to a larger wind farm, or if you go to a larger wind turbine, if you go from 3 megawatts to 6, you can install half of the machines. The costs per megawatt are usually somewhat equal. The foundations are slightly bigger. The maintenance is slightly more expensive, but it is not as expensive as installing twice as many monopiles. And the same happens if you go from 6 megawatts to 12. Where instead of installing 64 turbines, you can now install 16. And that means that overall, you save a lot of money on the balance of plant, on the operations and maintenance, on the per unit cost, and in the end, it gives you a cheaper project. And this is why, especially over the last couple of years, you see a lot of these wind turbine manufacturers leapfrogging over each other and trying to compete who can build the biggest wind turbine, because that is the way you land projects. This is not without challenges, of course. Building a big offshore wind turbine is difficult. There are a lot of challenges when it comes to manufacturing. So to the left, you see the 107-meter blade from General Electric. So that goes into the big. This is currently the biggest wind turbine blade in the world, and this is not easy to produce. What you see in the middle, that there is a joint where the two halves of the blade are molded separately and then joined together. And there are a lot of challenges that arise here, because, for example, if you want to glue these two halves together, then when you get to the other side with your glue gun, it might be the case that the glue has dried already at the beginning. So there are a lot of there's a lot of smart thinking needed here. And to the right, you see a monopile in our Northern wind farm. So Northern has monopiles of around 8 meters in diameter, and these two become bigger. And with it, you have the issue of finding suitable production plants in order to still be able to manufacturing these kinds of structures. But you also have the problem of, say, buckling that grows when these structures get bigger. And then in order to install these turbines, bigger turbines are also more difficult to install, because if you have a very big component, when you start to align the bolts with the bolt holes, for example, if you have a blade that is 107 meters long, it can be very difficult under windy conditions to align 100 bolt holes on the wind turbine hub, for example. And that means that where you would be able to install at 15 meters per second, for example, now your weather window has decreased, because even at 10 meters per second, the blade starts vibrating so heavily you cannot safely install anymore. And then with it, there is also once we start to build larger projects and further offshore, there's also the challenge of getting all the energy to shore. And this is a drawing of the German Blight. So this is an overview of all the wind farms offshore wind farms in West Germany that have been producing and are under development and are planned. And you see that Germany has a very awkward bit of North Sea, bit of clamped between the Netherlands and Denmark, and it means that also all the offshore wind energy has to enter Germany from a very narrow strip of beach. And that means that it is up to the transmission system operator to reinforce the onshore grid and to make sure that all the high voltage lines can deliver all of these extra gigawatts. And the same problem actually plays in the Netherlands. In the Netherlands, we are rapidly rolling out offshore wind, and all this energy has to be delivered at some point. And that means that in some cases where the onshore grid is already congested, it means that in the case of IJmuiden, for example, so that's in the west, you need to make a big detour, and in this case feed the energy into Zeeland. So that's to the southwest. And with so much wind power on the grid, it also means that you start to affect the electricity prices. So this is actual data from a month of January, a couple of years back, where you can clearly see that on the y-axis there is the electricity prices per megawatt hour, and this is basically the fluctuation around the mean. And on the right axis, there is wind speed. And you see that in very windy months, there is already so much wind energy on the grid that it starts to affect the electricity prices. So that means that if the wind speeds go up, basically the entirety of the Netherlands is producing wind power, and by that the prices go down, and vice versa. And you could, for example, see that a couple of times last year, where we had for example, a very sunny and windy weekend. I think it was Easter, for example, where you have a lot of solar power, a lot of wind power available, but there's not a lot of demand because everyone is staying at home or working at home with COVID. And you see that the supply massively outweighs the demand, and that the electricity prices are so heavily influenced that they even go negative at some point. And also, this is the slide that I promised you about space. So if you look at the North Sea area just outside of Delft, for example, this is the amount of sea that we have. These are the offshore wind farms that are under construction and that are planned. So at first glance, there might be a lot of sea space available, but you also share it, for example, with oil and gas companies. So all the lines here and dots, so all the lines are either offshore oil and gas pipelines, they are telecom cables, they are high voltage power cables. And all these dots are oil and gas platforms. If you then plot all the other zones, so in green there's sensitive nature zones. You share it with the military, for example. They need to practice somewhere. There are safety zones for helicopters landing on oil and gas platforms. And if you then also plot all the space that is reserved for shipping, for example, and you see that suddenly it doesn't look as spacious anymore. And you notice that you actually have to share a lot of space. So this is a drawing of the Hollandse Zuid 3 and 4 wind farm, where you can see that if you zoom in on an offshore wind site, then you see what happens with all of these cables and pipelines. So all these cables and pipelines, they have, for example, maintenance areas on both sides that essentially. So what essentially happens is that you're building a wind farm, but you're building a wind farm on top of existing infrastructure. And in case one of these telecom cables or pipelines fail in the field, then the owner needs to be able to repair and to inspect this. So in the Netherlands, that really means that you are sharing the offshore wind farms with for example, pleasure crafts, with the owners of pipelines and telecom cables, with fisheries, for example. And then this is actually the last slide that I want to share with you for today. So we've talked about scale, but this is a picture of the port of Esbjerg. So this is one of the, if not the major offshore wind hub in the world. And you see that there are a lot of wind turbine components laid out here. And what you see is that if we double the amount of offshore wind capacity every 3 years, it also means that we double the waste and we double the material usage of offshore wind every 3 years. And I think that is one of the major challenges that we still have for offshore wind. And I think that this is something that I want to invite you as students and people who might work in the field after your studies to really think about. Because I think it is important that we don't exchange a climate problem for a research problem or a resource problem. So with that, I want to thank you and to open the floor for Q&A.
Yes, thank you, Q&A. Very interesting. And indeed, there are some questions. Also, a good bridge to the last slide you mentioned is from Rahav Saini. He mentions recently in news, it was said that for revamping the wind farms in the US, nacelle will be replaced in the existing towers with new improved ones. Is this true? And is this actually currently being done regarding the waste you just mentioned?
Mhm. I haven't heard of this specific case myself, so I can understand that this is something that plays on land. So on land, you usually have a a size restriction that is very much governed by the local requirements, and there it could be easier to replace a wind turbine top with a similarly sized wind turbine top. So that is definitely feasible. If the tower itself has plenty of structural life left, then sure. If you talk about offshore, then the turbines grow so rapidly that in essence it will never be feasible to install a new wind turbine hub on an existing tower, just because it grows so quickly.
Okay, I think this answers the question. Also, another question from Rolf is, are the wind farms and turbines optimized by cost or by the energy generation per area?
So with wind farms, we optimize it usually based on the cost of energy. So that is the energy produced per euro. So that means that you are trying to strike the right balance between turbine size, between foundation and balance of plant costs, and other various other requirements. So wake losses, for example.
Okay. And Thorkel then asks, what types of software is used to optimize these wind farm layouts or designing projects?
Yeah, so we have our own in-house design suite. So we have our own software that we've programmed in MATLAB. That is a production model and optimization routine that we've developed over the years, and that features a lot of our own experience.
Okay. Then Mahu Misra asks, doesn't increasing dependence on a small number of larger turbines raise the risk profile while the balance of plant is improved? And how is this risk factor evaluated?
Yes and no. So if you install bigger turbines but fewer, it means that you have fewer components. So that means that you have fewer components that could fail, and so in that sense, the risk decreases. On the other hand, if something does fail, your components are bigger and more expensive. So it is in total net, it is the risk decreases, but the cost of failure increases.
Okay. Then Geert Wijnands asks, what is commonly seen as a tipping point for CO2 emission if you compare the creation of a wind platform with the comparable emission in the case of fossil fuels? And then take gas, for instance.
I think the energy payback time of I think it's several months. If you think about how much CO2 you emit during the fabrication of steel and installing the machines, I think the payback time of CO2 is several months. If you talk about cost of energy produced, then offshore wind is one of the cheapest electricity sources already. So an offshore wind farm that is newly constructed is cheaper than operating an already built fossil fuel plant.
Okay. Then Rolf has another question about the competition between smaller turbines versus large turbines. What are the technical difficulties and challenges of a 12 megawatt turbine wind farm? And is this outcompeting the more reliable smaller wind turbine farms of 2 megawatts?
Yeah, so what you see, apart from the economies of scale that you have working in your advantage, the problem of growing turbines time after time is that there is usually not a lot of experience with a single turbine platform. So what you see over the last couple of years is that turbines have been growing up to the point where you see a new turbine platform for a manufacturer coming out every 3 to 4 years, and accelerating. And that means that for every turbine type, there are only a couple hundreds of machines operating in the field. So there's not a lot of time to really gain experience with a single turbine. And that is really working against you. For very big machines, if you keep pushing the boundaries, you really don't have a lot of time to evaluate the design choices that you've made. So if you talk about very big machines, so for example the 12 megawatt turbines, they are reaching parts of the atmosphere that we don't really know a lot about. That might be a problem. We have blades of 107 meters long that bend, that are very flexible. So they bend in a way that perhaps current beam models could not predict. So those are challenges. And if every turbine you've installed is only preceded by maybe 50 turbines, then basically you're always installing a prototype, and that also comes with an increased risk profile. So, for example, if you're buying a car, you would be very, very confident buying a Volkswagen Golf because you know there are already millions of Volkswagen Golfs produced. But if you are the first one driving the new Tesla, then you know that you're going to see some problems.
I can understand. Okay, and also another question regarding the different wind turbine types from Cody Owen. Understanding the industry inertia regarding the horizontal axis wind turbines, but considering the problem of growing wind turbines offshore, is there an initiative to design and build vertical axis wind turbines?
I think so. I think that that you might see vertical axis wind turbines when you go towards floating platforms. So if you think about the bottom fixed, I think you probably see the propeller type machines very often, just because there's the projects are so big, so massive. You spend billions of euros on a single offshore wind project, it becomes very difficult to accept the risk of a completely new design. That being said, if you move towards floating, then you have a totally new ballgame. If you go towards floating, then if you look at the balance of plant costs of a floating foundation, these are way higher. The steel that goes into a floater is much more than a monopile, for example, and then it definitely it becomes a big differentiator how much weight you actually put on top. And a vertical axis machine with the generator and the entire drivetrain in the bottom, that could very well be much cheaper than a propeller type.
Yeah. Also, Yit Mandipa has a question. What kind of condition monitoring systems does most offshore wind turbine use?
Yeah, so every turbine, they are riddled with sensors. So we measure everything from loads to electrical voltages, winding temperatures, the temperatures in the bearings, everything, accelerations, everything feeds into a SCADA system that flows through the fiber optic cable. So all the inter-array cables that we have on the seabed, they all have a fiber optic connection in the center. And that is being fed onshore, and we can access that from a web interface. And that's where we get the data from.
Okay, thank you. Then Ariana has a follow-up question on the floating wind turbines. Since you have mentioned them, is Eneco actively doing research on the floating wind turbines and their challenges? Is Eneco involved somehow?
No, currently not. Currently not. So currently we are active primarily in the North Sea, and the North Sea, compared to other areas of the world, is a very friendly environment to offshore wind, because the water depths are never really deeper than 50 meters. It is a sandy soil, which is it's easy for pile driving. If you look at floating, then you think about areas such as France, for example, so southwestern France, or the Mediterranean, or Norway, or Japan, or East Coast or West Coast USA. So those are usually the areas that you go floating. Then companies usually involved in floating are companies like Equinor or Shell or.
Okay. And then Roy asked, what is your take on wind-based hybrid renewable power plants? Is Eneco doing any research in this area?
So if you talk about hybrid renewable power plants such as the Hollandse Kust Noord wind farm, then yes. So next to Hollandse Kust Noord, we have a very large innovation program attached to this that will run for 5 years, and that has all kinds of partners such as TU Delft, but also TNO, and I missed a couple of others. And that will be a wind farm where we will install battery and hydrogen storage, and we will also install a floating solar farm that will actually be connected to the rest of the wind farm. And with that, we can actually do research on what it actually means to have solar and wind coupled, and storage. So in that case, yes, we are heavily involved in research.
I also had a question, because the slide you mentioned was that the designated wind farm zone is very big compared to the existing wind farms currently built. What is your vision about the division of these zones? What is the year that you expect them to be divided or fully built on by these wind farms?
What do you mean?
Like the wind farms, the existing wind farms, is relatively small to the designated wind farm zone. What is your expectation in the upcoming years about the division of these wind farm zones?
Yeah, I get it. Yeah, so the designated wind farm zones, those are basically zones that the Dutch government has marked as being interesting to develop a wind farm on. Once they get closer to the actual tender, what you see often is that they shrink down the site, and that has to do with the fact that you are, as a wind farm, you are taking up a lot of space, and a space that cannot be used for fishery, for example. So in the Netherlands, currently leaving space for fishery is a big topic, also with the upcoming Brexit. So that means that it is up to the government here to decide how much area to reserve for wind farms, taking into account that if you shrink an area, we have more wake losses. On the other hand, leaving more room open for shipping, for fishery, for nature. And in the end, it is up to the government and the policymakers to strike a right balance between, on the one hand, the supply of electricity, and on the other hand, the how much the ecological system can bear, and how much room we need to save for other sectors.
Yeah, I can understand. Okay, thank you. Then there's one other question. What is likely the most favorable service support transport system for services in the future? Still by ship or repair by wire, in combination with drones? Or
I think that in the near future, so we are moving further and further offshore. I think in the near future, we will start to move away from the smaller high-speed vessels, so crew transfer vessels. These are the smaller boats that can where you can carry 10 to 12 people with 10 to 12 people with small components in the tool bag. And you will start seeing them being replaced by larger service and operation vessels. So those are bigger ships. They're usually also equipped with a crane, and they can operate in under higher waves, for example. But you also don't need a crane on every platform anymore, for example. I think you will start seeing smaller ships being overtaken by larger ships. I think when it comes to drones, I think there is definitely a role for drones. Definitely, if you talk about inspection, for example, replacing visual inspection by rope access with a drone, that is, in terms of safety, is to be preferred. If you talk about transporting stuff and repairing stuff with drones, I think there's still quite a way to go. And not only if you talk about the range and the carrying capacity of drones, but also the risk involved by having a projectile coming towards a multi-million euro machine at high speed, for example. So there are challenges.
Okay. Then I would like to wrap up the event with this final questions. Of course, everyone is interested. Are there any intern opportunities at Eneco currently, or do you have knowledge about any research group within Eneco that is looking for interns?
Yeah, so currently our offshore wind team is a very small team. So we do often have interns, usually one, maximum two. At the moment, we have an intern already working with us, but at least for this academic year, and for next academic year, there are probably new opportunities. But if you, I can always help or bring you into contact with people within the organization. If you have an idea on a master project that you want, you're looking for someone to spar with, or you have a supervisor from university, but you want to make sure if it has any industrial relevance, and then you can always contact me.
It's really good to know. So for everyone, I guess keep an eye on the website for the upcoming academic year, and then maybe you'll find something. Okay, René and the participants, thank you very much for your talk. I think everyone enjoyed it a lot. Thank you everyone for all the interesting questions and the interesting answers as well. Yes, of course, we hope to see you guys in the end of this week on Friday with our last event of the year. And for now, I would like to say thank you and have a good day. Okay.
Yeah, thank you.
Bye-bye.